Welcome back. Last episode, the determinant arrived as a signed volume, one number that tells you how a matrix scales space and whether it flips orientation. Today we make that number do work. First we learned cofactor expansion, also called Laplace expansion, a recipe that computes any determinant by breaking it into smaller ones. Then we gathered the algebraic properties, how row operations affect the determinant, why a matrix and its transpose agree, the product rule, and the triangular shortcut. With those in hand, two classical formulas drop out almost for free: Cramer's rule, which solves a linear system as a ratio of determinants, and the Adjugate formula, which builds a matrix inverse entirely out of cofactors. Both are gorgeous. Both are also slow. The cost explodes as the matrix grows. By the end, you will know these formulas cold and know exactly when not to use them. Two definitions power everything in this episode. Start with a square matrix. Pick an entry, say the entry in row I, column j. Now cross out that entire row and that entire column. What remains is a smaller square matrix, and its determinant is called the minor of that entry, written m sub ij. The cofactor is almost the same thing. With one twist, you attach a sign. The cofactor c sub ij equals -1 to the power I plus j times the minor. That sign follows a checkerboard pattern. Plus in the top left corner, then alternating plus, minus, plus as you step in any direction. So for a 3x3 matrix, the signs read plus, minus, plus across the top row, minus, plus, minus across the middle, and plus, minus, plus across the bottom. A minor is just a smaller determinant. A cofactor is that minor with a plus or minus glued on, and which sign you get depends only on the position, never on the numbers. Here is how cofactors compute a determinant. Pick any row of the matrix. Walk across it. For each entry, multiply the entry by its cofactor, that is, by the smaller determinant you get from deleting its row and column, with the checkerboard sign attached. Add up those products across the row, and the total is the determinant. That is cofactor expansion, or Laplace expansion. The beautiful part is that it does not matter which row you choose. Every row gives the same answer. And you are free to expand along a column instead of a row, with the same result. This freedom is a gift. Always pick the row or column with the most zeros, because every zero entry wipes out an entire smaller determinant before you ever compute it. Notice the method is recursive. An n by n determinant becomes n determinants of size n minus 1. Those break into still smaller ones all the way down to 2x2 blocks you can do by hand. Now the properties, and the most important ones, concern row operations, the same three moves we used in elimination. First, swapping two rows flips the sign of the determinant. Second, scaling a single row by a number c multiplies the determinant by that same c. Third, and most usefully, adding a multiple of one row to another row leaves the determinant completely unchanged. Hold on to that third one, because it is the key to fast computation. A few consequences fall out immediately. If two rows are equal, swapping them changes nothing yet must flip the sign, so the determinant equals its own negative, which forces it to be 0. If a whole row is 0, the determinant is 0. And the headline fact tying determinants to everything before, the determinant is 0 exactly when the matrix is singular, meaning it has no inverse and its columns are linearly dependent. A non-zero determinant means invertible. Three more properties, all structural. First, a matrix and its transpose have the same determinant. That single fact means every statement we make about rows is automatically true for columns, which is why cofactor expansion works down a column just as well as across a row. Second, the product rule. The determinant of a product equals the product of the determinants. This is remarkable. The determinant turns matrix multiplication, which is intricate, into ordinary number multiplication. From it, we get that the determinant of an inverse is 1 over the determinant, and the determinant of a matrix raised to a power k is the determinant raised to k. Third, the triangular shortcut. If a matrix is upper or lower triangular, its determinant is simply the product of the entries on its main diagonal. Now combine the last property with the row operation rules and you see the fast algorithm. Use elimination to reduce the matrix to triangular form, tracking sign flips from swaps, then multiply the diagonal. That is how determinants are actually computed. Here is the first payoff, Cramer's rule. Suppose you want to solve a square system, a times x equals b, where the coefficient matrix A is invertible, meaning its determinant is not 0. Cramer's rule writes each unknown as a ratio of two determinants. To find the ith unknown, take the matrix A, throw away its ith column, and slot the right-hand side vector b into that column instead. Call the result a sub I, then x sub I equals the determinant of a sub I divided by the determinant of A. One determinant in the numerator, the original determinant in the denominator, repeated for each unknown. Why does this work? If you expand the modified determinant along the column you replaced, and use the fact that the determinant is linear in each column separately, the algebra collapses exactly back into the original system. The catch is built in. The formula needs the determinant of A to be non-zero, which is precisely the condition that the system has one unique solution. The second payoff is a closed form for the inverse. Build a new matrix by replacing every entry with its cofactor. Call that the cofactor matrix. Now transpose it, swapping rows and columns. The result is called the adjugate of A, sometimes the classical adjunty. The inverse is then breathtakingly simple to state. A inverse equals 1 over the determinant of A times the adjugate. Every entry of the inverse is a cofactor divided by the determinant. Where does this come from? If you multiply A by its adjugate, something clean happens. Expanding along a matching row reproduces the determinant, while expanding along a mismatched row gives 0. That is a hidden identity about cofactors. So A times the adjugate equals the determinant times the identity matrix. Divide through by the determinant and you have the inverse. It is the most explicit inverse formula in all of linear algebra, and you will almost never use it for anything bigger than 3 by 3. Let's watch cofactor expansion happen on one canvas. At the top sits a 3 by 3 matrix, and we highlight its top row in gold. That is the row we will expand along. 3 arrows fan down, 1 from each top row entry. Follow the first arrow, delete the row and column of the first entry, and the 2 by 2 block that survives is its minor, drawn below with the crossed out row and column shown faint and gray. The second arrow does the same for the middle entry, the third for the last entry. Above each branch we mark its sign from the checkerboard, plus, then minus, then plus. At the bottom, everything assembles. The first entry times its plus minor, plus the second entry times its minus, minor, plus the third entry times its plus minor. Add those 3 signed products and you have the determinant. The whole method is right there in the picture. 3 entries, 3 smaller determinants, 3 alternating signs. Here is Cramer's rule as a single image. Picture a fraction. On the bottom sits the determinant of the original coefficient matrix A, drawn with vertical bars on each side. On the top sits almost the same matrix, but with one change. We have lifted out its second column and dropped the right-hand side vector b into that empty slot, shown in gold. Take the determinant of that modified matrix, divide by the determinant of the original, and the result is the second unknown, x sub 2. A small inset on the side shows the same maneuver for the first unknown. There you replace the first column with b instead. The pattern is clear and mechanical. To solve for any unknown, swap the matching column out for the right-hand side, take that determinant, and divide by the determinant you never touch. Beautiful to look at, and you can see why it costs a fresh determinant for every single unknown. First worked example, a 3 by 3 determinant by cofactor expansion. Take the matrix with rows 1, 2, 3, then 4, 5, 6, then 7, 8, 9. Expand along the top row using the signs plus, minus, plus. The first term is 1, times the 2 by 2 determinant of 5, 6 over 8, 9, which is 45 minus 48 equal to negative 3. The second term carries a minus sign, minus 2 times the determinant of 4, 6 over 7, 9, which is 36 minus 42 equal to negative 6. The third term is plus 3 times the determinant of 4, 5 over 7, 8, which is 32 minus 35 equal to negative 3. Now assemble. 1 times negative 3 gives negative 3, minus 2 times negative 6 gives plus 12, plus 3 times negative 3 gives negative 9. Add them. Negative 3 plus 12 minus 9 equals 0. The determinant is 0, so this matrix is singular. And indeed, the middle row is exactly the average of the top and bottom rows, so the rows are linearly dependent, exactly what a 0 determinant detects. Second worked example, Cramer's rule on a 2 by 2 system. The equations are 2x plus y equals 5 and x plus 3y equals 6. The coefficient matrix A has top row 2, 1, and bottom row 1, 3. The right-hand side B is 5, 6. Start with the determinant of A, 2 times 3 minus 1 times 1, which is 6 minus 1, equal to 5. That is our denominator. For x, replace the first column of A with B, giving the matrix with top row 5, 1, and bottom row 6, 3. Its determinant is 5 times 3 minus 1 times 6, which is 15 minus 6, equal to 9. So x is 9 over 5. For y, replace the second column with b instead, giving top row 2, 5, and bottom row 1, 6. Its determinant is 2 times 6 minus 5 times 1, which is 12 minus 5, equal to 7. So y is 7 over 5. Quick check, 2 times 9 fifths plus 7 fifths is 18 fifths plus 7 fifths, which is 25 over 5, equal to 5. The first equation holds, so the solution is correct. Third worked example, the inverse of a 2 by 2 matrix from the adjugate. Take A with top row 4, 3, and bottom row 6, 5. Its determinant is 4 times 5 minus 3 times 6, which is 20 minus 18, equal to 2. Now the cofactors. The cofactor of the top left entry is its minor, the lone entry 5, with a plus sign, so 5. The cofactor of the top right entry is the entry 6 with a minus sign, so -6. The cofactor of the bottom left entry is 3 with a minus sign, so -3. The cofactor of the bottom right entry is 4 with a plus sign, so 4. Lay these out as the cofactor matrix, then transpose to get the adjugate, top row 5, -3, bottom row -6, 4. Finally, multiply by 1 over the determinant, which is 1/2. The inverse has top row 5 halves, -3 halves, and bottom row -3, 2. For a 2x2, this matches the familiar shortcut: swap the diagonal entries, negate the off-diagonal ones, and divide by the determinant. So why the warning that these formulas are expensive? Count the work in cofactor expansion. An n by n determinant breaks into n determinants of size n-1, each of which breaks into n-1 more, and so on down. The total number of operations grows like n factorial, which is explosive. A 10 by 10 determinant by pure expansion already costs about 3.5 million terms. A 20 by 20 would need more terms than there have been seconds since the Big Bang. That is hopeless. Cramer's rule and the adjugate inherit the same curse because they call for many determinants. The fast way is elimination. Reducing a matrix to triangular form costs roughly n cubed over 3 operations, utterly manageable, and then the determinant is just the product of the pivots, with the sign for the row swaps you made. So treat Cramer's rule and the adjugate as theory, and as tools for tiny matrices by hand. For real computation, elimination wins every time. A little history, because these ideas are older than matrices themselves. Determinants appeared first, before anyone wrote a matrix as a grid. Around 1683, the Japanese mathematician Seki worked them out to solve systems of equations, and a decade later, in 1693, Leibniz arrived at the same idea independently in Europe. In 1750, Gabriel Cramer published the rule that carries his name, using it to pass a curve through a set of points. In the 1770s, Vandermonde and Laplace put cofactor expansion on a firm systematic footing, which is why we also call it Laplace expansion. Then, in 1812, Cauchy assembled the modern theory and proved the product rule in full generality. The determinant of a product equals the product of the determinants. Finally, in the 1850s, Arthur Cayley fused determinants and matrices into a single algebra, the language we use today. Notice the determinant predates the matrix by almost 2 centuries. Let's recap. Cofactor expansion, also called Laplace expansion, computes a determinant by summing each entry of a row or column times its cofactor, where a cofactor is a smaller determinant with a checkerboard sign. Choose the row or column with the most zeros. The row operations, swapping rows flips the sign. Scaling a row by c multiplies the determinant by c, and adding a multiple of one row to another leaves it unchanged. 3 structural identities. A matrix and its transpose share a determinant. The determinant of a product is the product of the determinants, and a triangular matrix has determinant equal to the product of its diagonal. The determinant is 0 exactly when the matrix is singular. Cramer's rule gives each unknown as the determinant of a column-swapped matrix over the determinant of the original. The inverse equals the adjugate divided by the determinant. And all of this, elegant as it is, costs about n factorial operations, so for serious work we reduce to triangular form by elimination. Next episode, we leave concrete matrices and define the abstract vector space itself. Today we turn the determinant into a toolkit. Cofactor expansion, also called Laplace expansion, computes a determinant by walking along any row or column, take each entry, multiply it by the smaller determinant you get from deleting that entry's row and column, and attach a plus or minus sign in a checkerboard pattern. Then the properties. Swapping 2 rows flips the sign. Adding a multiple of one row to another leaves the determinant unchanged. The single most useful fact, because it means elimination preserves the determinant up to the sign changes from swaps. A matrix and its transpose have the same determinant, so rows and columns play interchangeable roles. The determinant of a product equals the product of the determinants. And a triangular matrix has determinant equal to the product of its diagonal entries. From these, 2 classical formulas. Cramer's rule says each unknown equals a ratio of 2 determinants. Replace one column of the coefficient matrix with the right-hand side, take its determinant, and divide by the determinant of the original matrix. And the inverse equals 1 over the determinant times the adjugate, the transpose of the matrix of cofactors. Both are exact and elegant, and both cost roughly n factorial operations, so for real computation we use elimination instead. Worked examples: a 3x3 determinant by expansion equals 0, a 2x2 system solved by Cramer's rule, and a 2x2 inverse from the adjugate. Historically, the determinant grew from Leibniz and Seki in the late 1600s through Cramer in 1750 to Cauchy and Cayley in the 1800s. Next episode, we leave concrete matrices behind and define the abstract vector space. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.